For this next example, we want to find the x values, if any, at which the function is not continuous. So we're going to find points of discontinuity. We're going to find them both analytically and graphically. And then any discontinuities we want to address as to whether they are removable or not removable. So I have this function here, f of x equals x plus 3 over x squared plus 8x plus 15. And I've actually already graphed it, but let me just show it to you in Desmos. And here it is. So this is what this graph looks like. Lovely, isn't it? And now I went out of my way to kind of show the puncture, because there is a puncture, but there's also an asymptote. And I'm going to prove that to you right there at -5. And I'm going to prove that analytically. So let me go back to the document camera. Now, how in the world am I getting that? Well, I'm modifying my function. So I recognize that the denominator from algebra class is something that we've learned how to factor. So it's x plus 3, x plus 5. The x plus 3's, of course, will divide away, and that leaves me an equivalent expression, not exactly the same, but equivalent of 1 over x plus 5. Namely, it's equivalent everywhere except at -3. And actually, I ran into problems with that in Desmos. Let me just go back real quickly and show you in Desmos. So I wanted to graph the function so that you could see the open hole. So I graph it with a restricted domain. But I couldn't get the function, let me go here. I couldn't get it to recognize -3, comma, f of -3. It wouldn't graph a dot anywhere when I tried for this function being f of, here, if I called this f of x, for example. It just wouldn't do it and wouldn't do it. And I was getting very frustrated. And then I remembered, oh, right, of course it won't do it, because the function itself doesn't have a value at -3, because -3 would cause the denominator to be equal to 0. So it didn't like it. So what I had to use with the equivalent expression right here of g of x equals 1 over x plus 5 in order to get myself this little hole right there. Right? But that's where that hole is. So I can see that the function itself is not defined there. However, the puncture exists there. All right. So let me go back. So I drew a quick sketch of that. I kind of threw in my scale, although my scale got a little wonky down here at the bottom. This is -10 over here and 10 over here, roughly. And you can see you have a vertical asymptote at -5, and we have a hole at -3. So when we want to discuss places where this function is not continuous, what we want to say is that f of x is not continuous, right, is discontinuous at 2 values. So at x equals -3 and x equals -5. Now -3 is a removable discontinuity. There's a limit there, right? And that's what this equivalent expression is getting for us. So this is a removable discontinuity. That's because the x plus 3 divides away, right? In other words, the limit exists, right? The limit as x goes to -3 of f of x exists, right? But x equals -5 is non-removable discontinuity. Asymptotes always are, right? Because there's no limit. And there we go. So we found any x values where there's discontinuities, and we've addressed whether or not they are removable or not removable. All right, let's look at letter B. Now letter B is a little bit strange. It's called a step function. Well, it's the beginnings of a step function. So you have a horizontal line over here and a horizontal line over here. Now the reason this happens is, let me just address absolute values for just a second. And hopefully your pre-calculus or algebra instructors taught this to you. But the absolute value of x minus 1 is equal to 2 things. It's called a piecewise function. It's actually x minus 1 as long as x is greater than or equal to 1. In other words, x minus 1 is greater than or equal to 0. and then it's negative that whole or that whole function if x is less than 1. Right? So think about this. If I put in 2, 2 take away 1 is 1. 2 take away 1. 3 take away 1 is 2. 3 take, right? But if I do 0, let's just put 0 in. 0 take away 1 is -1, and the absolute value of -1 is 1. So I need negative 0 take away 1, negative -1. It works. This is how to define an absolute value function. Okay, so what does that mean for our function? So that means that f of x, I'm going to drive it this way. So f of x is equal to two functions. It's actually x minus 1 over x minus 1, which would be 1, right, if x is greater than or equal to 1. And it's negative parentheses x minus 1 over x minus 1, which would be -1 if x is less than 1. Right? I'm just using this definition of the absolute value right here to create my numerators. And I'm correct, right? So this is -1 here, this is 1 here. And if you don't believe me, Desmos will back me up, I swear. So let me just hide part A and put in part B, and there it is. Absolute value of x minus 1 over x minus 1. Done. And I actually just threw in some empty circles at the points just so you could see them. Right? But there they are. Actually, it looks like for this particular one, the way I've defined it is that I would have a open circle, and the reason I'm going to have an open circle on both of them is exactly what we're trying to get at, because this definition is fine with the greater than or equal to 1 for absolute values, but not for when you're dividing it, because when you're dividing, right, we got to be a little bit more careful because we can't have 1 itself is not in the denominator, or is not in the domain. So I actually have to erase that, sorry. We can't have it, right? X cannot be 1 itself, because if x was 1 itself, we would be dividing by 0 in the original function, and that's forbidden. So we could only have greater than 1 and less than 1. We can't have greater than or equal to. That's okay up here because there was no division, but it's not okay down here because we have a division. We have a rational expression. All right, now what does this mean? Well, you can see it in the graph and you can see it in here. We don't have a function value at 1. We can't because the function itself will be divided by 0. So this means that f of x is discontinuous it's the fact that these two numbers are not the same. That's kind of a clue, right? So f of x is discontinuous at x equals 1. You can tell it the limit values are different. So the limit coming in from the right is 1, the limit coming from the left is -1. And also there's no function values. So we actually violate all three conditions. So it's discontinuous because there's no function value and no limit. No f of 1 exists, and the limit as x goes to 1 of f of x does not exist as well. Right? F of 1 does not exist, and the limit does not exist. It's actually a violation of both. So it's a violation of all three of the continuity checklist items. Okay, but what kind of discontinuity is this? Removable or not? Well, if the limit doesn't exist, that's a non-removable discontinuity, right? The limit not existing means you're going different places. So this part right here means that it's a non-removable discontinuity. And there we have it.